today we start connecting the ideas of sufficiency back to, so we talked about sufficiency, minimal sufficiency, completeness. We talked a little bit about conditional expectation as projection. Today we're gonna go back to the idea that we started like the quarter with, that we care about minimizing the risk of estimators. And so the first idea or the first result that we're going to talk about is this so-called Rao-Blackwell theorem that connects the risk minimization with sufficiency. And it's a statement about convex loss functions. So remember, there's this loss function. The slides, do you see the slides now? I'm going to post the slides afterwards. Do you want the slides now? Is that? Yeah, so let me post it afterwards. It's going to be a little bit time consuming to do it now. So the Rao-Blackwell theorem is a statement about the convex loss functions. And so we first have to like understand or remind ourselves about convexity. So anyone has seen the idea of convexity, convex functions, convex sets? Can someone tell us what a convex function is or what a convex set is?
For a convex set, if you take two elements of the set and you add them together with a weight that's in 0, 1, and 1 minus that weight, then you get another element of the convex set.
Okay, so yeah, if I take two elements and I form this, I believe that's what you mean, right? So this would be an element in the line segment that connects them. So as you vary lambda from 0 to 1, you would trace this line. And so every point like that would be in the set. So basically any 2 points, geometrically any 2 points that you pick in the set, the line segment that is connecting those 2 points will be in the set as well. So this is an example of a convex set, so this is not, right? So if I take 2 points here, some parts of this line segment lies outside. So that's the set. And so convex, not convex. So what about a convex function? Yeah, go ahead. Someone wants one, two. So the function between 2 points lies below the line between the function points. Yeah, so basically if I have something like that, if I take 2 points, x1, this is going to be f of x1, and then I have x2, and then f of x2. If I connect these 2 points on the graph with a line, this line is entirely above the graph of the function between those 2 points. Okay, and something like this is not convex because if I do that, you would see that sort of I'm going to cross, some part is above, some part is below. So this is convex, this is not convex. Another way of connecting it is to connect back to the idea of sets. So there's this thing called the epigraph of the function, which is the set of all the points that are above the graph. And this is hard to draw. So this is the epigraph. So the epigraph of a function is the set of all x and t, this works in general, such that t is bigger than f of x. So this works if f is in Rn to the R. So every point x and t such that this is the epigraph. So everything above. So a function is convex if and only if this epigraph is a convex set, which you can easily say it's equivalent to the definition that we just said. So there's this nice connection between functions, convexity of functions and convexity of sets. So if you write that definition that the value of the function, so this is a general point between x and y. So these are the values of the function at those points. These are these things. These function values. And so these are the value of the function is below this. The convex this is called the convex combination lambda times 1 minus lambda. If you form the same convex combination of the values of the function, these are this is basically the value on the line. And so this is saying the line stays above the function. And so we have strict convexity if the inequality is strict, unless lambda is equal to 0 and 1. So if the graph of the function is strictly below that line segment or chord, everywhere except the endpoints. So if this holds over, usually you talk about convexity over a region or the entire, let's say RP. And so this has to hold for any pair of points. So we have the idea of convexity, we have the idea of strict convexity. An example of a function which is not strictly convex is this guy. Just the absolute value of x that you've seen in homework problems. This is convex, but it's not strictly convex. We can easily verify that. If I take 2 points here, the graph of the function basically is the same as this line segment. So it satisfies the inequality, but it's in fact equality. So it's not strict. So examples of loss functions. So we care about the loss functions as functions of the action, basically. So here's an example, the LP loss. And if p is bigger than or equal to 1, this is convex. If p is in 0 to 1, this is non-convex. And if p is strictly bigger than 1, this is going to be strictly convex. For p equal 1, this is the L1 loss, which is convex, but strictly convex. Okay, so we have a question. What is the relation between the convex set and the convex function? I gave you one relation, so you can define convex sets, and then you can define convex functions as functions whose epigraph, which is a set, is convex. That's one possible connection. There is, yeah, no problem. There's another way. So if you define a convex function like this, so in convex analysis, usually you allow the value of the function to also be infinite. And if you think about it, everything works in the extended, this is called the extended real numbers, or the set of extended real numbers. These inequalities make sense. So this could be infinite, this could be infinite, this could be finite, or both sides could be infinite. So inequality, if there's no negative infinity, then you don't run into issues of infinity minus infinity, which might be problematic to define. If you just let positive infinity, you're fine. So in convex analysis, usually you let that, so functions are extended value. And then there's this idea of a domain of a function. We'll see examples of this later in the course. So if the function is allowed to be taking values in this extended real line, then the domain of a function is called, is the set of all values for which the function is actually finite. And you can show, for example, that the domain of a convex function is a convex set. So this is one other connection. So the first connection that I mentioned is like basically defining convexity of functions in terms of convexity of sets. The other one is that once you have a convex function, the domain is a convex set. This you can verify from the definition of convexity and the domain. Okay, any other questions? Comments? So convexity is a very geometric idea, as you can see, and it's very intuitive, even in high dimensions. You can imagine, so convex sets and convex functions have simple forms, relatively simple forms. There are a lot of useful results about them, and optimization over them basically is well understood. And you've seen one example of it in your homework 1. It's a little tricky, but even in the non-smooth cases, you can do interesting things in terms of optimization. The thing that we are going to use here is a property of convex functions, which is very useful. It's so-called the Jensen or Jensen's inequality. Okay, so people know about the Jensen's inequality. How many people know about it or learned about it so far? Okay, a couple of people. Good. Okay, great. Seems like a good size of a good proportion of the class. Yeah. So the idea is basically what happens to the expectation if I move it inside a convex function. So if I have a convex function and apply it to a random variable, if I have f of e of x, it's easy to remember this way. If I pull it out, if it's a convex function, it gets bigger. So pulling the expectation out of a convex function makes it larger. And the easier way to see it is if f of x is x squared, if you don't remember the direction, expectation of, this is saying expectation of x squared is less than expectation of x squared, which is the inequality that says the variance is non-negative. So this you probably remember if you remember the formula, the alternative formula for the variance. And so pulling the expectation out of a convex function makes it generally bigger or bigger than or equal to. So there are some niceties here. So f needs to be convex on basically the support of the random variable x. So f is convex on S, and x takes the values in S with probability 1. So it could be that the random variable that you're looking up is concentrated on some part of the space. F is convex on that part, but not convex everywhere. This is still true. So this is useful to remember. These are probabilistic statements. You don't care about the behavior of the function outside the support of the distribution of x. And the only other condition is that the expectation of x be meaningful, so that x is integrable. So this condition implies that e of x makes sense. Makes sense. So this side makes sense. This side could be infinite. It's fine. The other thing is the conditional equality. So if the function is strictly convex, then equality holds if and only if x is equal to the expectation almost surely. In other words, x is constant. So when we're dealing with a strict function, so for example here, this is a strictly convex function. This Jensen's inequality that added claim here means that in this case, if I have equality here, then it means that the random variable is constant almost surely. And you know it in this case because in this case it means that the variance is 0. And you hopefully know that the random variable whose variance is 0 is constant. But this is sort of a generalization of that. If I have, for example, 1 over x is convex. We had this came up, or we had this come up earlier. So this is x, this is 1 over x. So the function x maps to 1 over x is convex on 0 to infinity. So if a random variable x takes values, so let's say probability that x is in 0 to infinity is 1. okay, 1 over x is not going to be convex over the entire region, but over the 0 to 1 is 0 to infinity is convex. So if I have a random variable which is non-negative almost surely, then we know that the expectation of 1 over expectation of x by Jensen is less than or equal to the expectation of 1 over x. This came up earlier in like analysis of those Poisson rate estimation, if you remember. And so if there's equality here, because this is a strictly convex function, it means that the random variable is constant. So if the random variable is genuinely random, non-constant, then this is going to be strict even. It's a very interesting result. So a strict unless x is constant. Okay, questions about the meaning of it? So the very basic case of this, where x takes two values with probability lambda and 1 minus lambda, is basically this. So if you write down that case, so if x takes values x and y with probability lambda and 1 minus lambda, if you write down the Jensen's inequality, that would be just the definition of convexity. So this is like a generalization of once you have it for 2 points, then you have it for any distribution. You can easily generalize it to like multiple points, but this is generalizing it even beyond that to like infinite, like uncountably many points. Okay, questions? I'm going to talk briefly about the proof because I believe your book also does it. There's a very nice proof of this. You don't need any fancy like PDFs, things like that. It's just very neat and it works in general. So this works in the general setting of any probability distribution. You don't need any assumptions beyond the fact that the expectation of x is finite. So the idea is a geometric one. So if you have a convex function, you can always let's say find, so if I pick a point, x0, and this is f of x0, I can always find a sort of supporting hyperplane. A supporting hyperplane is like a tangent hyperplane. In the R2, it would be just a line, right? So it touches the function, and at that point, and the function is above it. So that's the meaning of a supporting hyperplane. Or it's like sometimes called like, so this is called the largest affine minorant, basically. Minorant means it's below the function. So the largest affine minorant. So you have, for a general convex function, you have many many minorants. So you can have many affine functions that are below this. And you push one of them up until you hit this, that would be a supporting hyperplane. This for a general function, you can't. So if a function is like this, you can't have it like a affine minorant. It's going to cut the function. It's not always below. But for convex functions, you have these affine minorants, and the maximal ones are these supporting hyperplanes. So the reason why this is in general useful, there exists such a thing for any convex function, is that even if the function is not differentiable, you've seen examples of this. So this is also related to the idea of subdifferential, if you're interested, that I pointed out in the homework one. So if you have a convex function like this, at the point of non-differentiability, there are many affine minorants. So, and there are many supporting hyperplanes actually. So each subdifferential basically gives you the slope of one of these. So these supporting hyperplanes, when the function is differentiable, there is one, which is just a tangent one. But if it's not, there are many. The fact is that there is at least one for every convex function. At any point, you can find it. There's like minor conditions, but let's say if f is convex, you can find a supporting hyperplane. So I pick x0 and f of x0, there's a supporting hyperplane. X0 in our case, we're going to take it to be the expectation of x. This is a number, and a hyperplane in general would be like this. So there's this normal to it, which is that. And then x minus x0 plus this. The way that I've written this is it's an affine function, which is a hyperplane. And the way I said it is such that a of x0 is equal to f of x0. That's the part that we're touching. This you can easily verify the way I've written it. We know that it passes through x0 and fx0. So it touches the function. And for every x in S, f of x is bigger than or equal to this. So these two together mean that the first one means that it's a minorant, and this means that it touches the function. And so it is a supporting hyperplane. So there exists something like that. So I pick x0, I can find an A basically such that this holds. That's the only thing that you need to know, and this is like a fact of convex analysis. And if you're interested, it's related to these separation theorems, Hahn-Banach separation theorems. There are many variants of it. This is one like variation of it. In any case, so we have this. This is like from convexity, from convex analysis. There exists at least one such supporting hyperplane. And so I then take the expectation of both sides. So I take the expectation of both sides. Expectation is monotone. Monotone. And so we have this. And then I have this line, which is by the linearity of expectation. So if I put x here and then take the expectation, I can move the expectation inside here. Because of the linearity of expectation goes inside. Basically, this thing would be expectation of x minus x0, but x0 is like by our choice is equal to x expectation of x. So this term is going to vanish. And so you get this. And we have shown that f of x is bigger than or equal to f of x0, and x0 is just expectation of x. Right, so this we have shown is bigger than this, which is just the statement of the result. So it's a very simple proof. Uses the existence of supporting hyperplanes and linearity expectation. But it's a very far-reaching result. The strict convexity would imply that you can also see from the geometry that this supporting hyperplane sort of inequality is true strictly unless x is equal to x naught. And because if x is not equal to x naught with positive probability, so the probability that this is not equal to x naught is bigger than 0, this only can happen if x is not constant almost surely. Then with positive probability, would have when you replace the random variable, this would be true with positive probability because that would be just so this is saying x not equal x0 implies f of x bigger than a of x. So the implication, probabilistic implication, is that this is less than or equal to probability of f of x bigger than a of x. So logical implication translates to this, and we know that this side by assumption is positive because x is not constant. then this holds with positive probability. And when things hold with positive probability, when you take the expectation, if inequality is strict with positive probability, then the expectation is strict. So the monotonicity expectation, this is a property of the integral. If this inequality holds, so basically if the random variable is positive with positive probability, then the expectation is positive probability. So that's probability expectation. So this holds strictly. So we have shown that if the random variable is non-constant and the function is strictly convex, then the Jensen's inequality holds strictly. Of course, if it's constant, it's easy to see that it's just equality. So the proof is complete. Any questions? Comments? All good? Okay. So I spent a bit of time on this, but the ideas are interesting, and this inequality is very useful, as you might have also seen in the first homework and later. So now to go back to the Rao-Blackwell, so we recall this decision theoretic setup. There's this loss function. There's a decision rule, an estimator, and then there's the risk, which is the expected loss. So Rao-Blackwell says something like this. Suppose T is sufficient. T is a sufficient statistic for a family P. We have an underlying probability family, right? So this is the set of P theta, theta being in omega, and T is T of X. So the setup is, again, just X is drawn from this. So X is like P theta. And then delta X is a possibly randomized decision rule. So I'm going to talk about this. For now, let's say it's just non-randomized if you want, but the result holds for more general cases. And A2, this loss, the function, the loss as a function of the action is convex for all values of theta. Then we can define an estimator. So given an estimator delta and a sufficient statistic, we can define a new estimator. So if you recall this conditional expectation, this is like a projection of delta onto T, the best approximation of delta by that sufficient statistic. So this, by definition, if you recall, is going to be a function of T. So it's a new estimator, which is only a function of the sufficient statistic. Then this eta will dominate delta. So Rao-Blackwell says that basically eta is a better estimator delta, or at least as good. So as good as delta in terms of the risk. The risk is almost like, not almost, everywhere for all values of theta is below or equal to delta. And in particular, if the loss is really convex, for example, the quadratic loss is like that, then the inequality is strict unless eta is equal to delta almost everywhere. So eta being equal to delta means that delta was just a function of the sufficient statistic from the start. If delta was a function of the sufficient statistic, then when you do this conditioning, it's in that space of functions of T, so it comes out. Remember the projection idea. So if delta is already a function of T, then eta would be equal to delta, and so this is vacuous. But if delta genuinely contains some other things other than the T, then this would be different from eta, and so you'd have a strict inequality. So you strictly do better, which means that the delta in that case would be inadmissible. Does that make sense? So this is in a strong sense, justifying why sufficiency is important from a decision theoretic perspective. So you only want to form estimators that are functions of a sufficient statistic. If you carry more information, I can always basically find a better estimator. So this procedure is some sort of a smoothing out or averaging. So you basically average delta over the level sets of T, basically. So whatever information there is, which is noise, I'm going to average out over the values of t. So for any t, given if t is equal to t, if the estimator is a function of t, it would be fixed. If the estimator is not a function of t, delta would have would be variable, would be random still given t. And this procedure is averaging out that randomness over the value of t equal to t. And so that new estimator, which averages out over the values of t, is better. It's going to do better. So if you contemplate this result, it's a very interesting result that tells you exactly that sufficiency is meaningful from a statistical perspective or from a decision theoretic perspective. Questions about the statement? Okay, so the only place in this theorem and the proof that we're going to use sufficiency is actually to say that eta is well defined. So anyone, I used this statement before when we talked about completeness. Anyone remembers what I mean by eta is well defined? So eta is well defined by sufficiency of t. So what do I mean by that? Its definition does not depend on parameter theta, so it's a statistic. Great, yeah. So in general, when you take this conditional expectation, because we are working with a family of probability models or for probability distributions, the expectation is taken under one of these, and so it depends on which one you do take the expectation under. So this is in general depends on theta. So in general, I should write eta of t and theta. But that wouldn't be a proper statistic because it depends on the unknown parameter. Sufficiency allows me to say that this guy, because this is dependent on x, so we know that the conditional distribution of x given t is invariant to theta. So it's not functionally dependent on theta. So this expectation is going to be invariant to theta. So it's just going to be a function of t almost surely, and that makes this a value statistic. So that's the only place actually that we're going to use sufficiency. So eta is a valid statistic, and the next step is to show that the risk is basically below or equal to the risk of delta. And for that, we're going to apply the Jensen's inequality. So I've written it here. So if I form L theta and then expectation of, so I can apply the Jensen conditional on something. It's just conditional expectation is similar to the expectation in that sense. So I have the conditional expectation here. So you can mentally remove conditional on t if it bothers you. This is true. So think of this operation as a new conditional expectation as a new expectation operator. So this works if I condition on something else everywhere, right? So I can works by replacing, or let's say for conditional expectations, I can say expectation of f of x given t is bigger than or equal to f of expectation of x given t. Okay, conditioning you can ignore. And that's basically what we're going to do. So I'm going to do this, and then I pull out the expectation because in the second argument I'm convex. I can pull it out and get a bigger value. So L theta and delta, but conditional on t. And then I take so this is by definition eta. And then I take the expectation of both sides. And this one simplifies by the property of conditional expectation, which is what? Anyone? Yeah, this would be the expectation of L theta delta by the smoothing or tower property. So, or iterated expectation, basically, if you want. And so this side is just the risk of delta. This other side is the risk of eta. So this is just an application of Jensen's inequality. And this statement is again an application of the strict statement in the Jensen's inequality, which I leave you to verify. Okay, so this result is basically application of the Jensen's inequality conditional on the sufficient statistic. Questions? So this procedure of conditioning on insufficient statistic is sometimes called Raoul equalization. So Raoul equalization, like for obvious reasons. It's a hard, like a fancy way of saying I will condition on the sufficient statistic to produce a better estimate.
Professor, could you possibly return to when you first introduced Jensen's inequality? You just rewrote it with conditional expectations. I didn't get a chance. So, okay, perfect. Thank you.
Yeah. Do you have any questions about this, or?
I just needed to write it down.
Okay. Yeah, you can just replace the expectation everywhere with conditional expectation on a bunch of variables.
Yeah, makes sense.
That would work.
Right, thank you.
No problem. Any other questions? So I mentioned randomized estimators. Anyone knows what I mean here? So the estimators we have seen so far are non-randomized. So they're deterministic functions of x. So what do we mean by randomized? So sometimes randomization is helpful. This result is saying it's not helpful. So by randomization, we can extend the class of decision rules. So one thing that you can, like a simple way of saying it is that delta, so randomized rules is really a function of x and some u. This is an external source of randomness. Whose distribution does not depend on theta. Yeah, so maybe it involves a random variable in the function. Yeah, so you can basically exactly. So it's like a function of both x and u. So once you determine, once you observe x, the delta, the rule is not perfectly deterministic. So still, for example, you flip a coin and decide. So I observe x, flip a coin, and based on the result, I decide. Or I observe x, draw a random uniform random variable 0, 1, and based on the values. Another way of saying it is that you can think of delta x as being random, and the rule just specifies what is the distribution of this. So given x, so you specify what is the chance that, so once you've conditioned on x, there is the randomness in this, but you specify what is the chance that delta x is in some interval. Either way is fine. This is a little bit more explicit. But we'll see examples of this maybe. Sometimes it's useful. Raoul-Blackwell theorem is that saying that for convex functions, it's not helpful. So if you randomize, that randomness is going to be removed once you do the expectation. So you expect, when you take the expectation, this is an external sort of part, something that's not function of the t. So this is obviously cannot be written as a function of t. Once you take the expectation, you smooth that out. So you basically average that out. And as a result, it would be as if you didn't have that randomness from the start. So this is saying, even if you extend or enlarge the class of decision rules to include randomized decision rules, you cannot beat an estimator, which is just a function of sufficient statistic. So if you do that, I can always come up with something which is, this is deterministic. Basically, it's saying that deterministic rules are good enough. So I can, if you've come up with a randomized estimator, I can construct a deterministic estimator just based on the t, such that I beat you, or at least do as good as you. Especially for the like quadratic laws, the strict convexity makes it even more significant. So this result is saying that anything that's not like a strict function or proper function of sufficient statistic is going to be inadmissible. So because of the inequality being strict, it would be inadmissible. Questions, comments?
So deterministic in this case just means deterministic conditional on having observed X.
Yeah. So that's, yeah.
Okay.
The decision rule is basically a function of the observation. Right. You can think of the decision rule as just a flat function, right? Not the random variable. So this is like the value. The value is random, but the decision rule is the functional relation. If you want to think of that, there's no need to condition. So decision rule is not, this is just the value of the decision rule at the current observation. But the decision rule itself is like a deterministic rule. Here, the decision rule is a randomized rule. Does that make sense?
Yeah. I think on the homework you have a problem where it's like the form of the decision rule depends on what value X takes on or your data takes on. But in that case, it wouldn't be random. It would be deterministic because you're conditioning on X.
Not sure what you mean. But if the form depends on X, basically overall, there's going to be a function of X. Maybe we can talk about that problem.
That makes sense.
Right, yeah. So yeah, in the end, there is going to be either a deterministic rule from the set of observations to the decisions, or that cannot be done, and there's an external social randomness, then that rule would be like a random function. Here, the rule is like a deterministic function. So that's another way of sort of saying it. Okay, any other questions? Okay, so here we have a tricky example. So we're looking at that uniform example that we have been looking at in the past couple of examples, let's say. It's like one of our running examples. The xi's are IID from uniform 0 to theta. We know that t is sufficient, and in fact, we know that it's complete. We show that it's a complete sufficient statistic. Sufficiency follows from the factorization theorem, if you recall. And that's the only thing we need here. So suppose I take delta to be the average of xi. So let me ask you, is this a good estimate of theta? Is the average a good estimate of theta?
No, it's consistent for the not the endpoint.
So what is it consistent for?
The theta over 2.
Great, yeah. So if we want to have a good estimator for theta, we could multiply it by 2, right? That would be a better estimator. So, but this is a not so good estimator, like has a bias, big bias. But what I want to show you is that it's fine, and you can even improve this by doing, you just pick any estimator. It doesn't have to be the good estimator. And then do the raw molecularization, which is form this estimator. So we have an estimator, which is not quite good. And even if I do this, a better estimator, this is not a function of sufficient statistics, solely a function of sufficient statistics. So raw Blackwell tells me that I can improve it for the quadratic loss. But let's work with this. You can, in the end, multiply by 2 if you want. But if I want to do the raw Blackwell, I would form this expectation. Okay, expectation of delta given t. This will strictly dominate delta for any strictly convex loss function. So we want to verify this. We want to compute the risks of these estimators and see what happens. In order to do that, I have to be able to compute this conditional expectation, and this is where we run into these sort of measured theoretic issues that you have to deal with the distributions that are not continuous. These are singular distributions. So let me try to give you an idea. So suppose I have, so if I have this, if I divide xi by theta, what would I get? Uniform in 0 to 1. Yeah. So it's easier to work with these variables from a probabilistic perspective. If I want to compute the conditional expectation, it's easier to work with these. So I'm gonna, let's say, assume either I've divided by theta, or let's say take theta to be 1 for now, equivalently. So let's say I'm in the 2-dimensional case. These are uniform in 0 to 1. So if I want to represent the distribution as like a distribution of mass, basically, in the plane, it would be like uniform in this square. In general, it would be unit cube. Okay, so what I need to do in order to compute these expectations, I need to figure out what is the distribution of x1, x2 given t, which is the maximum of x1 and x2. If I figure out the joint distribution, then I can do these calculations. I would actually need marginal distributions, but let's figure out the joint distribution first because it's easier. So suppose I condition on t being equal to t. And I want to figure out what the joint distribution is. Let's make this bigger. So how do we compute the joint distribution of x1 and x2 given t equal t? Like describe, compute might be a little bit more ambitious. One of x1 and x2 has to be t, and the other one will vary from 0 to t. Okay, great. So that's exactly what will happen, because the maximum, basically t equal to t, the location is either x1 is equal to t, right? X1 is the maximum, which is going to be equal to t, in which case x2 could be from 0 up to t, can be bigger than t, otherwise the maximum would be the other one. Or x2 is t, in which case the other guy has to be from 0 to t. Okay, so the conditional distribution would be supported on this. So all the mass would be here. And you can easily sort of argue for yourself that I'm restricting the entire mass to this piece. And so it would be uniform on this piece. So this would be uniform on this set of all x1, x2, such that x1 is equal to t and x2 is in 0 to t, or x2 is equal to t and x1 is in 0 to t. Okay, it's a uniform distribution in this, which is it's just hard to describe any other way. It doesn't have any density with respect to the Lebesgue two-dimensional Lebesgue measure, but it's what it is. Okay, so it's uniform on this. Now, if I want to compute the marginal uniformity, because the mass is uniformly distributed everywhere on 0 to 1, right? Once I condition, I basically restrict myself. So the mass, there is no lump of mass anywhere here, so it has to be uniform on this and on this. So it's sort of by some sort of a symmetry. So suppose I want to compute the conditional expectation of x1 given t. How can I get it from this joint distribution? Anyone? Once you have a joint distribution, how do you compute the marginals? Either x1 is equal to t, or x1 is uniform 0 to t, yes. But this is not the whole story. So what is the chance, for example, that x1 is equal to t? One half since they're IID. Yes, one half. So to see it from this, it's like by symmetry is obvious, but to see it from this, I have to collapse this entire thing in this direction. I have to collapse it to the x-axis. So when I collapse to the x-axis, this entire line, this whole thing is going to collapse to t. And this whole thing just comes down as is. Okay, so everything here is going to collapse to t, and the rest is going to like collapse to this part. So because things are uniform, one half of the mass is on this and one half is on this. So this entire one half of mass is going to be concentrated at this point. The rest of the one half is uniformly distributed here. So this distribution would be one half uniform 0 to t plus one half a point mass at t. Okay, you see like the idea. The geometrically is clear because these two pieces contain equal portions. When I collapse them, that's what's going to happen. Everyone sees this geometric idea. So if you understand this, you can reason about like the case where you have three variables. And if someone asks you what is the joint distribution of x1 and x2. So once you collapse, so the distribution would, in the three-dimensional case, would be supported on like a surface like this. Once you collapse, you get, for example, this sheets come down like that, and then you'd have something like this. So the marginal distributions in the general case would be interesting. Yeah, delta t, anyone knows what I mean by delta t? Anyone remembers this notation? If you recall the empirical distribution slides. It's not a step function, it's a measure. It's a probability measure. The CDF would be a step function. But delta t, delta of x in general means a point mass. A point mass. The point mass at t. It's not, yeah, Dirac function, it's like the measure. So it's a probability measure. It's like the equivalent of Dirac function if you work with the measure theory. So delta T of A is 1 T in A. So it's just a point mass at T. So it's a measure. It means like assign things to find through two sets. So if you pick a set that contains T, it would be 1. If you pick a set that does not contain T, it would be 0. So it's the probability distribution, basically. Distribution of a random variable that takes value T with probability 1. Okay, so it's a distribution of a very, like, let's say, degenerate random variable. Just takes the single value. And this is a notation of a mixture. So the distribution of a mixture of a uniform and a delta, the point mass. You can say Dirac, but it's not like the infinite. It's not the physics Dirac. It's like the measure theoretic Dirac. It's a well-defined measure. It's a very simple measure. Does that make sense to people? Go back to the slides that I talk about the empirical distribution. Should be clear there. Okay. If you understand this, then you can argue with in the general case, and you should get that the marginal distribution of x I given t would be 1 over n of mass would be at t, and the rest would be a uniform. So this is another way of writing xi given t is 1 over n delta t plus 1 minus 1 over n uniform in 0 to t. That's the distribution of the general case. There's 1 over n chance that xi is the maximum. And in the other case, it would be uniform 0 to t. That's what I wrote here. And when you compute the expectation, when I try to compute the expectation of this, expectation is linear. So what I get is eta is basically 1 over n expectation of xi, summation over I, expectation of xi given t. And by symmetry, these are all the same. So it's like expectation of one of them given t. So that's why I need to compute these marginal distributions. So the expectation of one of them, let's say x1 or xi, and if I have a mixture distribution, basically the expectation is it makes the same mixture of the expectation. So 1 over n plus the expectation of this, which is t, and 1 minus 1 over n the expectation of this, which is t over 2. A mixture distribution is basically like there is an extra variable that I'm conditioning on if you want. But hopefully it's clear to people. So the expectation is 1 with probability 1 over n, I take value t. With probability 1 over minus 1 over n, I get the distribution from this, whose mean is t over 2. And I'll let you argue that when you have a mixture, the expectation is just a mixture of the expectations. Okay, and so this simplifies to that. Questions? Okay, so that's the end result. If you consider the quadratic loss, the Rao-Blackwell says that you have strict dominance. So they strictly dominate the original estimator, which is delta. So this estimator is always going to have the same bias as the original estimate. Anyone knows why? So the Rao-Blackwellized estimator will have the same bias as the original estimator. Anyone? tower property, yeah. So if you take the expectation of both sides, you'd see that the expectation of two estimators is the same by the tower property. So the bias is the same. So in order to compare the quadratic loss, we just have to worry about the variances. So you can compute the variance of basically the variance of t is it's a maximum of a bunch of uniform. It's just you can easily compute it to be theta squared. So sorry, the average 1 over n summation I from 1 to n xi. So the variance of this would be 1 over n variance of one of them, and this is easy to compute. It's like theta 2 over 12. That's the variance of a uniform distribution of 0 to t. So that's the variance of delta. And for the variance of t, we get this squared. This comes out, and the variance of theta. Sorry, the variance of t. And t over theta is going to be beta and 1. This is a known result about the order statistics of the uniform. So verify for yourself. And so the variance you can look up on Wikipedia, the variance of a beta distribution is like that. So things would simplify to this. And you can see very clear improvement. So we go from the rate 1 over n to, this is like O of 1 over n. This is O of 1 over n squared. So this goes down like 1 over n squared. Asymptotically, this is like n. This is like n. So 1 over n squared versus 1 over n. So this is much faster. So the variance goes down like much faster. So the improvement is not insignificant. It's really significant. And if you compare the actual unbiased version, which is if I multiply this by 2, the estimator would be unbiased. And both estimators, the resulting estimator, so I would get this 2 removed here, and the variances would be multiplied by a factor of 4. So I get theta squared over 3, and here the 4 would go away. And you still see that then like the entire MSE, because the bias is 0, the entire MSE would be equal to the variance. And you see that you have a very significant improvement of the MSE. Does that make sense? Like, it doesn't have to make sense, but it's just, does it like, is it understandable? It's not obvious that this happens. And this is, in fact, the parametric rate. This is what you usually expect the MSE or the variance to go down. Like the quadratic loss, with the quadratic loss, you generally expect things to go down like 1 over n. This is an anomaly. So it's like something which is like not expected. It's like, this is super efficient at estimating the extreme. Questions? Comments? Is this clear? So this is Rao-Blackwell verify in this case. Rao-Blackwell says that it's better to form an estimator based on the maximum, not the average. And the maximum, in fact, beats the average by a factor of n in terms of the MSE, which is really interesting. Okay, there is a result here about strictly convex loss functions, which I'm going to skip. You're welcome to read. I'm going to skip this. Here's an example where Rao-Blackwell fails. So if the loss is non-convex, everything fails, could fail, not necessarily fails. But. So here's an example. Suppose you have a binomial. Yeah, I see that Some people are enthusiastic in the chat. Yeah, it's a cool example. So now in the previous one, so this one is also cool, but in a different way. X is binomial n and theta. This is like once you do sufficiency reduction. So in the Bernoulli trials, we know that the sum is sufficient. So you can reduce your model by just looking at the sufficient statistic. So the model in terms of the sufficient statistic would be this. So by sufficiency reduction, this is a problem of estimating the probability of a coin flip, like n trials of a coin flip. And then the action space and the parameter space are 0 to 1. I'll take the loss to be this epsilon sensitive loss, which is this thing. Suppose I have A, and this is theta. It's like a 0-1 loss, but only active if I'm epsilon away. So if I'm epsilon away from theta, I'm going to pay a loss of 1. But within epsilon of theta, I'm not going to pay any price. So I tolerate epsilon error around theta with 0 penalty, and then I jump to 1, like the loss jumps to 1. And so consider a general deterministic estimator. So a general deterministic estimator is a rule that assigns to every possible value of the observation x one value, let's say in 0 to 1. And this can be viewed as a vector or a set of values, delta 0, delta 1, up to delta n. Okay, so a rule is determined by specifying these n numbers. What value should I assign to each one of them? And so it takes at most n plus 1 values, the rule. So we can divide the 0, 1 to basically bins of length 2 epsilon. So I do 2 epsilon sort of divisions here. So I divide it into bins, 2 epsilon each. The length of each one is 2 epsilon. And take, assume, let's say n is 1 over 2 epsilon. This is like an integer for simplicity, and it's bigger than n plus 1. So epsilon is small enough such that this n is bigger than the sample size plus 2. So there's this little argument that you can do that at least one of the n bins contains no delta I. The midpoint of that bin is a distance bigger than epsilon from any delta I. Because there are n, so this is bigger than, so there's at least n plus 2 bins, and there are at most n plus 1 values. One of these is like a pigeonhole property. One of, if you distribute like delta 0 up to delta n is somewhere, they're somewhere in 0 to 1, and they fall within one of these bins. But because there are more bins than these guys, at least one of the bins would be empty. And if the bin is like this, then the midpoint of this, because the size is 2 epsilon, the midpoint is at least epsilon apart from any delta. So the deltas are, so at most they're here, and the other bins or elsewhere. The distance is at least epsilon to any other delta. And so that means that if you look at the epsilon sensitive loss, right, so remember you're looking at this delta x, right? For that value of x, that puts delta in that, sorry, not that's for that. So because one of the bins is empty, so want to say. So what we're looking at is the expectation of this, right? And I want to take the supreme of the max risk over 0 to 1. So what this statement is saying is that for every theta basically that I take, this risk is going to be not for every theta, but there exists a theta such that for any delta, so this means that there exists a theta in 0 to 1, such that for every delta decision rule, R of delta, or in other words, it's the other way around. So for every delta decision rule, there exists a theta bigger than 0, or sorry, 0 to 1, such that R theta and delta is 1. So why is that? Because for every delta, there is one of these beams that is not, there's empty. And so the distance to any other, the midpoint of this, which is, pick theta to be that. So that's my theta here. I'm going to pick that, assume that the true theta is there. For that theta, the epsilon sensitive loss would be 1, no matter what value delta t takes. So for this one, basically L epsilon theta delta x would be 1 almost surely, because it holds for all values of x. And so there exists a theta such that this is 1, because there exists such a thing, so the supremum is 1. And so this like logically means is equivalent to that. So the maximum risk is 1 for any the deterministic rule, non-randomized rule, and for sufficiently small epsilon, so epsilon satisfying this. On the other hand, if I take a randomized rule that just throws the data out and just set delta to be just uniform 0, 1, just randomly estimate, independent of x, the value of theta, then the risk would be just, the expectation would be just the probability, right? So this is just the probability that theta minus delta x is bigger than epsilon. And so you get delta x in this case, or delta prime x is u, so you get this probability. And this probability you can verify is less than 1 minus epsilon. I'll let you figure this out. It's easy calculation. So this is uniform 0 to 1. This probability is going to be less than or equal to 1 minus epsilon. And the worst case are at theta equals 0 and 1. So for any theta, this is less than or equal to 1 minus epsilon. So the supremum is less than or equal to 1 minus epsilon. So the sup over this is basically 1 minus epsilon and is better than 1. And so this randomized decision rule, which is like naive, basically outperforms every deterministic decision rule in terms of the maximum risk. And so this violates the All-Black rule result, but the All-Black rule result is still true because the loss is not convex. Okay. Questions, comments? Okay, so we're out of time. Sorry, again, for going a little bit over time. We'll come back next time and talk about another consequence of these ideas of sufficiency and completeness, which is the idea of uniform minimum variance and biased estimation. Okay, I'm going to stop here.